Hey everyone, welcome to iTower. Today we're tackling one of those classic interview questions that looks simple at first but hides a lot of complexity underneath. We're going to implement an LRU cache, which stands for least recently used cache, and trust me, this is one of those must-know data structure patterns for interviews at companies like Google, Meta, and even smaller startups. So what exactly is an LRU cache? Imagine you're working on a system with limited memory. You want to store values and access them quickly, but you also need to make sure you don't use more space than allowed. So when the cache gets full, you remove the item that hasn't been used in the longest time. That's what LRU means, least recently used. Now, here's where it gets interesting. The challenge is not just to store data and remove old entries, but to do it efficiently, in a way that both reading and writing operations happen in constant time. That's the tricky part. You need to be smart about how you manage insertion order and deletion. Many developers might try using an object or array, but those don't offer the same efficiency across all operations. We'll be using a map, and I'll explain why in a moment. But before we start coding, if you like videos that go deep into real interview problems and show you not just the what, but also the why, make sure to like this video and subscribe to the channel. It really helps iTower grow and lets me keep bringing you more content like this. Alright, let's build it from scratch. We'll start with a class called LRU Cache, and we'll initialize it with a given capacity. We store the maximum number of items allowed, and we use a map to hold the key value pairs. Now here's why we choose map. Unlike plain objects, maps in JavaScript maintain insertion order. This means the first item in the map is always the oldest one, the one we inserted first, unless we delete and reinsert it, and that's going to be a key part of our strategy. Let's add the get method. We first check if the key exists in the map. If not, we return -1. That's just convention from platforms like LeetCode. Now, if the key exists, we want to update its position to mark it as recently used. This is critical, and this is one place where people make a mistake in interviews. They forget that reading a value from the cache should also mark it as recently used. We get the value, remove the key, and then reinsert it. Why? Because deleting and reinserting will move it to the end of the map, which we'll treat as the most recently used side. The map keeps order by insertion, not access, so you have to do this manually. Let's move on to the put method. This one is a little trickier because it needs to handle both updates and evictions. If the key already exists, we remove it first. That's important because if we don't, and we just reassign it, it stays in the same position in the map. That would mess up the order and break the whole LRU logic. Then we insert the new key value pair at the end of the map, making it the most recently used item. Now for the eviction logic. Here's the heart of the algorithm. If the size of the cache exceeds the allowed capacity, we remove the oldest key. And here's a cool trick. When you call cache keys, it gives you an iterator of all the keys in order. Calling next value gives us the first key, the least recently used one. Now, a lot of developers forget this step or try to use arrays to track the keys separately, which overcomplicates things. But using a map like this is both elegant and efficient. Let's test our implementation and verify that it behaves correctly. We create a cache with a capacity of 2. We insert 1 and 2. Then we access 1, making it recently used. When we add 3, the least recently used is 2, so it gets evicted. Then we add 4, which evicts 1. In the end, 3 and 4 are the last 2 remaining in the cache, exactly what we expect. This code is clean and performant. But let me point out a couple of deeper things you might be asked in interviews. Could we use a weak map instead of a map? The answer is no. Weak map keys must be objects, and they don't maintain order. So we lose both our requirements. What's the time complexity? Every operation here, get, put, delete, and access to the first key, is O of 1 in map. That's because map is implemented internally as a hash table, with an ordered doubly linked list under the hood to track the order. Could we improve it? Yes, in more advanced versions of this problem, you might be asked to implement it using a doubly linked list and a hash map for full control over memory, especially in languages like C++ or Java. But in JavaScript, map does the job beautifully. And that's how you build a fully working, efficient LRU cache in JavaScript, the kind of solution that both works in real systems and passes interviews with flying colors. If you found this breakdown helpful, give it a like and subscribe for more deep dives like this one. Thanks for watching, see you in the next video.